All right, so what is the plan for today? I will start with some challenges in non-convex optimization, which, just to give some highlights, and then I will move on to particle-based methods for global optimization, give an overview. Afterwards, I will dig deeper into consensus-based optimization, and then at the end, I will give some ideas of how to kind of incorporate also gradient or higher order information in these kind of methods. So that's the plan. And yep, so yeah, what I'm looking at, or what we are looking at today, is basically this kind of problem, which looks very innocent in some sense when you write it down, but can be pretty complicated if you want to solve it. And so we have a function from Rd. D can be very high dimensional to R plus. This is an assumption, but in optimization, you can always shift such that this is fulfilled. And we assume continuity in order to get evaluations and be safe on this side. And now the difficulty of this problem depends strongly on the information available, or what do you want in the end from your solution. So one perspective you can take is what is the structure of the function. And then, of course, if you have convexity, it's a lot easier. If you have prior knowledge about the local location of the minimizer, then you can give a sophisticated start point and maybe help the algorithm a bit. If you have smoothness and can go even to derivatives, it gives you additional information. Or, as we just heard, it's also interesting to just consider a black box, so you can have evaluations but nothing else, and then it can be a bit more difficult. Another perspective or question you can ask is, what is the interest of the user? So if you say, okay, a local minimum is just fine, I want to get better than I am now, but I don't need the global one, then you have different methods at hand than if you really want to go for the global optimum. And also, what computational complexity is okay for you? Is it okay to compute a gradient? Can you even go to the Hessian or higher order, or is it not available at all? These are all things that you can take into account by deciding on which method you want to use for minimization. So yeah, let's go to the very or simple problem that you can think of. So the x square, it's convex. You have gradient info available very easily, and with the step size control, the gradient descent will do the job. So I say, joking a little bit, that if you have a method that is not able to solve the x square minimization, then you shouldn't call it optimizer. So this is really kind of the benchmark problem. And yeah, but even here, you know that gradient descent does the job, but very slowly. So you can think of methods how to speed this up. And there, for example, curvature helps, or doing a very sophisticated choice of step size will help. So this is the simplest problem, but we want to go to non-convex. So one non-convex problem is, for example, this one, where you have two global minima which have the same value. So here you can say, okay, I'm just interested in a global minima, and I don't care in which one I end up. So if I end up here or here, I don't care, but I don't want to end up here or somewhere else. So then I have a local convex problem. It's also called multimodal because I have here these two minima. If you have gradient info available, you can do a gradient descent, but you're not sure in which of these minima you will end up. So if you don't care, your gradient descent is still good. If you do care, then it gets more difficult. And one question also is, are there methods that are available to find both, maybe, so that I can not even just find a global minima, but I get also an information of how many global minima are inside a function, but this is the very, very difficult. And then going one step further, we just shift this one minimum a little bit so that we have one global minimum and one local minimum. Still, we have local convexity, you have gradient info, and then gradient descent may find a local or a global minimum, depending on your step size control and on your starting point, and you will never know where you end up. So you can tailor, for example, things where you start here, and then your intuition will tell you, okay, I go here, but it can be that for some reasons you end up here. So basically the gradient descent algorithm never tells you where exactly you go. It just says, okay, if I terminate, it's in a stationary point. And so in the very worst case, it can also end up here. Yeah? So yeah, gradient descent is the most common, or at least here we teach it to all the first year students, but I also like to point out that there are drawbacks, and there are it can be very difficult if you go to really global minimizers and not just local ones. So how to overcome local minima? This is of course a question that you can ask. And if we first assume that gradient information is available and your interest is finding a good local minimum, which is maybe not the first one you see, but a better one, but maybe still not the global minimum, then I want to highlight two ideas. So one is momentum enhanced gradient schemes, like the heavy ball or Nesterov method. And then instead of just going with the first order dynamics, or just a derivative kind of in position, you include a momentum term, and this allows you to overcome local minima and go further. Which is important to have in mind is that you are not sure that you go to a global minimum then. It's just that you are able to overcome local and you end up somewhere else, but it could also be that you go back at some point. So here it may help, but you're still not sure that you end up in a global minimum. And another idea, which is now very famous in all these AI and learning things, are stochastic enhancements. So you look at stochastic gradient descent, especially in high-dimensional problems. It's based on random batches. So you just take partial gradient information, and this gives you some noise, and the noise may help you to get to better local minimum, or you even combine this with momentum again and get these kind of Adam schemes. And here then the idea is to overcome the local minima by means of noise. Of course, this raises a lot of questions. For example, how to choose the batches. You can do this random. You can maybe set up some strategies, but it's really hard to prove for a range of problems that the strategy you choose really does a good job. Then what are requirements for convergence proofs is natural questions if you want to analyze your algorithm. And the question, are we finding maybe a better local or really a global minimum? And this is also very difficult to consider or to analyze. So this is if you have gradient information. Now let's forget about gradients and say, okay, we have just evaluations available. So at a point, I can ask for the function value, and I can ask also on multiple points, but the evaluation is all I have. And my interest is to find a global minimum. So I'm not happy with the local one. I really want to find the global one. And there are many, many heuristics on the market. It started, I would say, with genetic algorithms. So this is really inspired by biology. So you have kind of a parents' population, and they mate, and then the fittest survive, and the fittest in our sense are the ones with the lowest cost function value. And then kind of the process moves on, and you get from one generation to the next better and better function values. And then there are some tweaks and twitches to find really a wide spread of the state space in order to really search for the global one. And it turns out that in industry it's widely used and it does a good job, but from a mathematical point of view, there are not many proofs that this really converges. It's just practically it shows good results, but proving that it works, it's very difficult. Then there's simulated annealing. This is more now based on physics, not on biology so much. So here the idea is to kind of mimic a cooling procedure. So kind of the cost function gives you a landscape, and then you have a particle jumping around in this landscape and a temperature. And this temperature kind of tells you if you accept positions that are worse than your previous position. So if you cool down this temperature, you get more and more conservative and you are less willing to accept bad positions. So that means if the temperature goes kind of to zero, you will only jump to better positions. And here there are some proofs of convergence available. And yeah, this is a nice method, which is also related later on to consensus-based. I will show you later. And then I want to mention a zoo, not go into details of animal-inspired heuristics. So there are also some critique that basically for every animal you can invent a new method. Here you have to be maybe a bit careful. Yeah, but yeah, I want to mention that there's a lot on the market. And then I call it now particle-based method, even though you can also consider these others here kind of as particles, because if you do function evaluations and you call the spot where you do this evaluation by the position of a particle, then this is very close. But I hope later on I will give you more an idea why I clustered it like that. So the most famous particle-based method, I guess, is particle swarm optimization. This is also inspired by physics or by swarms. So here you have a lot of particles and they are able to interact. And every particle tracks the local and the global best information. Local means my personal best and global means the best position of the swarm. And then by random interactions, they explore the landscape of the function. And then at some point you stop and the global position should be a good approximation of the method. So this also works in practice very, very nice. But since you just have to stop at some point and take the best position that you have seen, also it's not so easily tractable from an analysis point of view. Then there are ensemble Kalman methods, which are based on Kalman filter and also kind of perform very nice if you consider kind of these inverse problems and yeah, have linear structure, then especially they work nice. And then there are consensus-based dynamics, which we started to work on some years ago and kind of tried to go to the essence. And this is what I want to explain you now in more details. So the main goal of consensus-based dynamics is to formulate the dynamics as differential equations. We want to have a provably convergent scheme, and we want to understand the main ingredients of global optimization algorithms. This is what I mean by essence, to know what dynamics we kind of require to have a good structure for global optimization. Yeah, this is a good time to stop and ask if you have questions at the moment before I move on to the next part.
We'll jump in. Does anyone have any questions before we move on? You can put them in the chat and I can read them out as well. Chance. Okay, I guess it's all quiet. So maybe we'll keep going.
Good. Great. So then we move on to the next one. So consensus-based optimization is joint work with many, many people. It started during my PhD in Kaiserslautern, mainly with René Pinnau and Oliver C. and Stefan Martin, who then left to industry. And then I went to Imperial College to work with Jose Carrillo and Yang-Pil Choi. And then basically the first two papers appeared and started kind of this adventure. So what is consensus-based optimization? We go back to this problem here. So we have our function f. We want to find the global minimizer, and we assume that it's unique. For the proof, this is also important. Now there are generalizations where they also look at multimodal, but for the starting point, we really assume that there's a global minimum, like here, one global, but many, many local. The function can be very nasty. So this is what we look at. And the task we said was we want to construct an algorithm that finds the global minimizer of f. Okay. Simple as that. And then we said, okay, we want some more requirements. So we really want to find the global minimum. I said that. We don't want to use gradient info, so just evaluations. And then we want to have different perspectives on the problem. So we wanted to write down a particle scheme, which is easy to implement and performs pretty good. But we made sure that there are indistinguishable particles, because this allows us to go kind of to theory and use a mean field equation, so kind of an average, and sending the number of particles to infinity. And this mean field equation, which is a partial differential equation, then we can use for analysis. So basically, we have then a whole family of problems. On the one hand, kind of the particle scheme, which is good for implementation and algorithms. And on the other hand, the PDE analog of this, which is good for analysis. And since we want to do analysis, we cannot do it too complicated. So we had kind of to play around a little bit and have a trade-off between simplicity, such that we can do analysis, but also efficiency, so that we have an algorithm that kind of does the job. So this was what we wanted to look at. And this mean field, of course, stems from a very different kind of mathematical physics point of view, where a lot of theory is available, that we moved now kind of into the optimization community, starting with these works. So what is consensus-based optimization? We wrote it down like that. So it's a stochastic differential equation, which consists mainly of two terms. We have here one deterministic term. And if I'm particle xi, then this deterministic term just tells me, okay, I move into the direction of Vf, whatever Vf is for the moment. And then there's also a random stochastic part here. And we have a Brownian motion, which allows us to explore. And this is scaled again by the distance of my position and Vf. So what does that mean? That means if I'm far away from Vf, then I explore a lot, because the Brownian motion is amplified a lot and I explore the space. But if I'm close to Vf, or even at the position Vf, then this prefactor is 0 and the exploration stops. If we look at this part, then also this part is 0 if xi and Vf coincide. So then the whole dynamics is 0 and I really stop. And this is important because you can imagine now, okay, this guy drives me towards Vf, and this guy explores. And then I have two parameters, the lambda and the sigma. And if I have them tailored, then hopefully when time goes to infinity, we explored the whole landscape, and we collapse at a point. So this is basically the idea. We need the two terms that are kind of mimicked in all these global optimization terms in different ways. So we want to explore by the Brownian motion, and we want to kind of share the information and collapse such that we get a stationary point at the end where all the particles meet, and then basically it's done. But from a net analytical point of view, of course, it's not simple to show first that this happens. And we want to collapse at the right spot. Yeah, this is the other difficulty. And here comes into, here comes into the play, what is VF? I just said, okay, we go in direction of VF. And VF is the weighted average, written down like that. But what is important here is this, so the weight factor. So what is hidden here? We have an exponential to make everything positive and to make this really an average, okay? And then we have minus alpha f. Recall, we assumed that f is positive. So that means if you take the exponential of minus alpha f, then particles with a good position, so a low function value, have a lot of weight here. And particles which have a very high evaluation have less weight. So that means this weighted average is an approximation of the best position that a particle sees at the moment. And of course you can ask now, okay, this is very complicated for just choosing the best position at the moment. But we do this in order to really pass to the mean field limit, because there every particle has to be indistinguishable. So saying, okay, you are the best particle at the moment, is not allowed if you have the plan to go to the mean field limit, because once you say, okay, you are the best particles, the particles are not indistinguishable anymore. So kind of this weighted average is taking a detour. We want to have an approximation of the global best, but we do not assign this to a particle. Okay, so that's the main idea. And what is nice now is, okay, this is an SDE. It's okay, it's a bit complicated because of the structure with the weighted average, because this makes it non-local and also non-linear because of f and the exponential. But you can use your favorite stochastic solver for stochastic differential equations. So for example, I usually just use Euler-Maruyama. Then I have a discretization of this guy, and I can implement. And if I take the VF from using the information of the last time step, then the interactions scale only linear. Even kind of every particle is communicating which the others with the weighted mean. Kind of once I computed VF, these other things are more or less linear. So this is a nice thing. And what is also hidden behind here is that we have Laplace principle at hand. So there is already theory that tells us if we send the alpha to infinity, then this weighted average is really converging to the global best. So this gives us already kind of mathematical structure or a theorem that we can use to be sure that in the limit alpha to infinity, our approximation works well, which is nice. Okay, let me go back here to give you an example of what happens. So now the blue particles are the particles xi for, I don't know, I think it's 5 here. And the orange one is the VF, so the approximation of the global best. And now if I let this run, then basically you see the solution of the SDE mapped into the cost function. So we see that this guy does not move at the beginning, and then the particles explore, but at some point they converge or collapse to one spot, and the spot is at the right location. Let's look at this again. So we have this particle, they are interacting via the SDE. At the beginning, this is the approximation of the global best, and then if you look at it again, at some point this particle, it's dragged towards here, and by going here, it visited this global minimum, and then kind of this local the approximation jumps here, and then the collapse happens. Okay, let's look again. Yeah. So yeah, that's the thing. One thing that is kind of yeah, kind of some pointing already to the last part is, if you notice that the global best is found pretty soon, but then it takes time until the collapse happens. And basically, the last part of this talk, I want to show you some ideas of how this can be sped up, such that this convergence happens quicker once you found the best position. But before we go to this, let's look at some results from the theory. So I told you, okay, theory happens on the mean field equation. So here is what this is. So we send n to infinity. So the number of particles is now infinity, and then kind of this SDE, which looks like the one for one particle, is kind of an average now. And it's a stochastic process called McKean nonlinear process. And this is now the information of the whole distribution of particles. So we send n to infinity. We put a little weight on each of the particles with the weight 1 over n. And then in the limit, our particle distribution converges to a distribution in a probability space. And kind of this dynamics tells us what is the characteristic of this process. No, this is a process, but it's a characteristic of this distribution. We see here the definition of the weighted mean. It's still the average, but now with integrals, of course. And having this structure, we can equivalently write this down as a non-local and non-linear PDE. Looking like that, we have here the diffusion part, now scaled with x minus vf squared, coming from Ito formula that you get the squares. And here the drift part, where you see that kind of you drift again towards the vf. And having this structure, we can prove now that we converge, so that the method really does the job. I put it here just very informally. So if f is bounded or growing fast outside of a ball, then and has a unique minimizer, then this distribution really concentrates arbitrarily close to the global minimizer as time goes to infinity. So this is basically what we aim at. So we have our distribution. We are allowed to explore the space, but when time goes on and on and on, we want to have a collapse and then at the right spot. And just to give you a sketch of the proof very, very quickly, it's basically 3 steps. The step 1 is the concentration, so the collapse at a spot. And this is done by just tracking the variance of the crowd. So we show that the variance of the crowd goes to 0 as time goes to infinity. And to get this result, you have to play a little bit with the 2 parameters, the lambda and the sigma. And if they have a good relation, then you can prove that this goes to 0. So that means you collapse, but you don't know where. So then in a second step, we show that this concentration point, the x naught, is still a real number as time goes to infinity. It could, so why we do that? It could be that this point travels towards infinity for t to infinity, and this is of course not what we want. So we show in the second step that this concentration point is finite, that our mass does not travel to infinity. And in a third step, here comes now the Laplace principle into the game. We show that for alpha to infinity, the concentration is located at the global minimizer. So for alpha, of course, in numerics, you cannot set alpha to infinity, but very big. And then Laplace principle tells you that you are in a good approximation of the global minimizer. Yep, so this is the result, and kind of it was our goal to give some analysis to the method. That's why we had to make it very simple, but it still works quite good in application. There are a lot of variants now on the market. I just want to give you an overview and say some words about sampling, because this comes later also into the game. So some colleagues proposed a slightly different scheme. So this one here for sampling, and the main change is this guy here, which is a matrix. It's the covariance matrix that you can set up by the different positions of the particles. And this covariance matrix, in combination with the prefactor theta here, if you choose the prefactor depending on the alpha which you use in the weight, you prevent collapse. So for sampling, the task is not to collapse, but to mimic a probability distribution of your target, right? So you want to prevent collapse, and this is done by setting the covariance matrix here. If you change the theta a little bit, then you will have collapse, and you have an alternative method for optimization. This is also what they point out. And yeah, so you can use a similar method also for sampling. There were proven a lot of links to particle swarm, to genetic algorithms, and to simulated annealing by other colleagues. So they really kind of say, okay, we see the similar behavior of this exploration and concentration also in these other algorithms, and replacing basically the global best with the approximation allows to do also some analysis there. Then often you have constraint problems, so there are also some variants of CBO with constraints. And yeah, then I would say the latest trend is called to parameter dependent and also to infinite dimensional problems now, but this is really very recent, but just to mention it. So the overarching goal is always to propose new methods, but also be able to prove something. Yeah, and this yeah, is a nice playground to work in. Yes. Here I want to advertise a little bit our software program. So together with some colleagues, we teamed up, and we provide some GitHub repository, so you can play around with this CBO. There are pre-implemented examples for neural network training. Polarized is for this multimodal problem where you have different minima. Then the sampling, of course, and also you can tailor your own noise. If you say, okay, this Brownian motion is boring, I want to have it more complicated, you can also put there your favorite noise. And then in 2D, this is example from this GitHub. You can see how this works. So the orange one is again the global best approximation, and the blue ones are the particles. And then you can see, even if you start somewhere else, they wobble around and explore the landscape. And yeah, very often you're happy enough or lucky enough that the particles see the best spot, and then it takes some time, but they converge to the right spot. So to be very clear and honest here, there's a little cheat, you could say, by passing to the mean field limit. So of course, if you do particles, you just have approximation of your probability density, and this you will only find the global best if one of the particles moves over the global best. Yeah, otherwise you have no chance. And this is kind of hidden in the mean field, because if you send the number of particles to infinity and you have the Brownian motion or the diffusion in your PDE, then instantaneously your distribution will cover the whole domain. And once you cover the whole domain, you will see every point. That means you can also see the global best point. And then the weight factor will help you to keep this point and just move everyone there over time. Yeah. So this is kind of why the convergence proof works so good. So in the mean field limit, by the diffusion, you just see the whole state space and therefore also the global best. You would never implement the mean field equation. Of course, the particle scheme is much more efficient, but you have to be lucky somehow that you have a good approximation of your distribution and that one of the particles really passes over the global best such that it's seen. Otherwise, you have no chance that the algorithm sees it. But I guess that's the same for all the particle-based methods. Okay, are there questions on this part?
Yeah. Any questions before we move on? We'll have time for questions at the end as well. Peter, yeah, go ahead.
Yeah, just wondering if you're doing end-to-end training with CBO, are you keeping a copy of lots of copies of every weight in the neural net? Is that because essentially that's what a particle is?
Yeah, you have to do that. Yeah.
Okay.
So this is very costly. For large neural networks, it's very costly. Yeah, because it's very high dimensional then.
All right, thanks.
You're welcome. Okay, so now, as I already motivated, it takes a bit of time until the convergence happens, and we know that the gradient or higher order information can help speed up this convergence. So together with Claudia Schillings and Philipp Wacker, we discussed a little bit how having all the particles moving around, we get some information of the landscape that we barely use at the moment because we just focus on the best particle more or less. So the idea was here, and it's kind of independent. You can use it for every particle method, how to infer gradient or even higher order information. And there, the task is, as I said, we are not the only ones doing that. Of course, there are simple gradients which kind of follow the same task, least squares regression, polynomial regression, and so on. Why we still follow this is because the way we tailored it is that we can approximate arbitrary high order of derivatives. We do kind of the same approach for all derivatives. We have error estimates using Taylor. We can have a trade-off between localization and globalization that I will show in a minute and is very helpful. And you can also sample derivatives. So what's the idea here? So we have our function, now it's called V, and we have an ensemble, like all the particles with their evaluations at some point. And the task is to find a good mapping from these knowledge of the evaluations to the gradient. Of course, this is the gradient at one point of the ensemble. This is, of course, an ill-posed problem, but we will do some assumptions and end up with a solvable problem. And this is our approach. So we say, okay, we do a Taylor expansion. So we write down this difference using basically the gradient, the Hessian, and then the higher order terms we put here. And here we put some random variable to kind of mimic the error that we do here. And now we even approximate the gradient and the Hessian by these expressions. So we say the gradient at xj is a sum with some coefficients that we will determine later. And these coefficients are just kind of linear combinations then at the end of these differences. And similar for the Hessian, we have the prefactor that are still unknown, but we said we want to approximate the Hessian by these differences here. And in these differences, just the positions of our particles pop up. So this is kind of a rank 1 approximation, and this is why it scales quite good. So yeah, we have the gradient, which is just a linear combination of these terms, and the Hessian is a rank 1, and that says directly that the additional terms that we have to consider are just scale linearly in the size of the ensemble, instead of, if you want to do the real Hessian, we have here quadratic, and for higher order even worse. Yeah, what is also nice, at least in my point of view, you can argue about that, is if your ensemble size, so the number of particles, is less than the dimension of your state space, then you do not infer information that you don't have. So having this approach, the gradient of V is always in the span of the ensemble. So if you don't have data, you don't do weird assumptions or things you don't have your hands on into the inference, which I think is reasonable. Of course, you can be lucky, but yeah, I think that's good. And some problems we have to address is, of course, we do all these differences here. And if you recall, if you want to use it for CBO, then at the end, the particles collapse. So then the particles get very, very close, and we can run in trouble with these terms. So we have to prevent overfitting at some point and numerical instabilities for the implementation. And we played around a little bit by this. So this is really trial and error. There's no analysis and theory behind. But it turned out that adding this sigma here helps a lot. And this sigma, this xi, I will call slack term in the following, and we will see in the numerical results the influence of this one. So now some notation, you don't have to recall it, it's just kind of vectorizing everything. And if you do that, then you can write down the problem that I just introduced, because we still have to find the prefactors of the Hessian and the gradient. You can write this down as an inverse problem. So you have here a matrix A that depends on your linear combinations and so on of your ensemble states. And then you have here a matrix times a noise term. And this is just the usual thing that you have in inverse problems. So you can use your favorite least squares or Bayesian sampling approach to solve it. So this is very nice. And kind of my collaborators have the background in inverse problems. So for them, this was kind of, yeah, an easy task. And yeah, having this, now let's kind of enhance our CBO with an additional gradient term, but of course not the real gradient, because we still want to have a black box problem, but a gradient approximation based on the inference that we did. Then we have different advantages. So we can explore an extended region, and we have a speed up of the concentration. And in numerical examples, that looks like that. So if we have this slack term 0, then kind of we have a local approximation of the function. So here we have the approximation for every member of the ensemble. So we see here these purple lines are kind of the approximation of the gradient of this point, or of this and this and this point. Of course, you have to do then a lot of computations if you want to have the gradient for all particles. If you do it at just one particle, then yeah, you get this info, which is not very helpful, of course. But if you use the slack term and set here this value to 1000, then it changes. So here again, we do the approximation for each member of the ensemble, and we see that the overall behavior is kind of a good indicator of the overall behavior of the cost function. And even if you do it just for one particle, like here, you get the overall structure of the cost function. So basically, you forget about all these wiggles, you get a nice picture of in which direction you should move, given your current direction. And just some numerical examples. So only 3 particles. If you do the standard CBO, there's no hope that you will find the true minimum here. You will just end up here in the best position that you have seen. Even if you run multiple samples, there's no hope. But if you enhance with the gradient, then you get kind of an idea of the overall structure, and you get better, and some runs really find even the global minimum if you start with these points. So kind of far away from the true minimizer, and a lot of local minima that you have to overcome. And yeah, if you do several runs, you can even go a bit better. And since I said that this is very general, you can also use it to replace the gradient or Hessians in every kind of method that you like. Yeah. So for example, the Langevin sampler, or Metropolis Langevin, or yeah, the whole slew of sampling methods that depends on derivatives we played around with. And here we only use 2 particles. Okay, that's pretty bad. But if you use 20 particles, then yeah, it works okay, I would say. So it really helps to get better. Of course, 20 particles is still not much, but yeah, on the other hand, you don't want to waste too much computational effort. Yep, and with that, I want to close. And yeah, here are the main references. Here is again the online resources. And yeah, thank you very much for your attention.